Okay, welcome back, everybody. So last time I had ended with a discussion of tilings of the plane. So forget about interior design or any kind of maybe artistic interest in tiling of the plane. Well, maybe don't totally forget about it. I mean, that might be one reason why you're interested in questions about this. So the example I gave last time was imagine that this paper is the plane, and imagine tiling this paper. So I'm going to do a little portion of it, right? So we'll measure out this chunk of our plane here, and imagine tiling this thing by squares. Right, so this is going to be really, really bad drawing because I have not. I would have to move to get my my ruler. So imagine a tiling by squares. So imagine that these are actually, squares. So in this tiling, pay attention to what happens at every vertex. Okay, so you might ask, like, why are you not, say, tiling by something else other than squares? So what if I take a chunk of the plane, and instead of tiling like this, I just kind of tile it by maybe things that look like this, right? So maybe I allow this kind of thing. Okay, there, right? Something like, and who knows, right? Well, so the reason for this, while this might look maybe cooler in your opinion than tiling things with squares, so I was going to keep. At some point in time, I started doing triangles here. I figured I would keep that. So let's, why might I do this rather than this? So there is. This wasn't always an explicit thing that the Greeks did, but this was something that comes up again and again in early Greek mathematics. Is the notion of almost treating this as rules of a game, although they weren't always explicitly stated like this, as we saw for a lot of the rationale behind these rules or restrictions were because there was religious significance tied in with some of these objects, and so something like a square, right? Let me pick one that actually looks more like a square. Oh man, I did a really terrible job. So anyway, something like a square or an equilateral triangle was inherently nicer to the Greeks than some thing that they didn't even have a name for, like this. And so while tiling the plane like this might be possible, what was interesting was a question of tiling the plane with regular polygons. So something like this is no good. I want to tiling the plane with regular polygons. And of course, what is a regular polygon? So a regular polygon, so all sides are congruent and all angles are congruent. Right. So all the side lengths are the same length, and all of the angle measurements are the same measurement. Okay. And so this is the notion of a regular polygon. Okay, and so, of course, what immediately concerns us is if we look at what happens at a vertex, in the case of a tiling by squares, well, a square is going to have 4 equal sides and 4 equal angles. Each of those angles is going to be 90 degrees, we know, because there's 4 of them. And, of course, those 4 angles, 90 plus 90 plus 90 plus 90, is 360 degrees, right? Again, we're being influenced by Babylonians here. This is 360 degrees. And in fact, that has to be the case because if this sum was less than 360 degrees, what would happen? This tiling would have a gap, right? So if we just kind of imagine what would happen in a theoretical tiling of the plane by regular polygons, so we don't know, this is for this is when my side is, there's 4 sides to my polygon. But say we don't actually know how many sides there are, then I have some number of angles meeting, right? And say I stop here, right? So I have 1, 2, 3, 4, 5, 6 polygons that they need to be regular. Of course, I'll worry about that later. So 6 of these polygons meet at a vertex, but whatever the interior angle sum, and all these angles should be equal, by the way, whatever the interior angle sum is, it doesn't sum to 360 because this bit is missing. Okay, and so we need that sum to be 360. Now, how can we dictate this mathematically? Right? How can we make sure that this is the case? Well, first of all, in a regular p-gon, what is the measurement of a single angle? All right, this is important to know. Well, we know what it is in a triangle, right? So if P is equal to 3, that's a triangle. A regular triangle is an equilateral triangle. And in that case, we know that the angle measurement is 60 degrees, right? So we know that this is 60, 60, 60. Why do we know that? Well, it has 3 sides. The sum of the interior angles of a triangle has to be 180. So I have 3 angles added together. That's dictated, of course, by the number of sides. So 3 angles, they must sum to 180. So this is 180 divided by 3, right? Okay. Well, what about a regular fourgon, right? So for a regular fourgon, what's the story? So here's a square. I know that for a regular fourgon, this has to be 90, 90, 90, 90. Why? All right. So again, 4 is the total number of angles. What's the interior angle sum? So we already know that the interior angle sum is 360, right? And so I get 90. But how did I know that, right? This seems like circular reasoning. The way I knew this is the second you see a square or a regular fourgon, hey, you can split a fourgon as 2 triangles. And each triangle has interior angle sum 180. So the total interior angle sum is 2 times 180 degrees, which is 360 degrees. This process can be used even for a regular fivegon. So let's see what happens there. So real quick, just to remind yourself, I'm not saying that these edges are necessarily going to be equal, but we'll try. This is also bad, but it's okay. Okay, so what's more important here is just showing how this process works. I'm not saying this is necessarily a regular fivegon, but the point is that any fivegon can be split into 3 triangles in the same way, right? So what is the interior angle sum of a regular fivegon? It is 5 minus 3, or sorry, 5, not 5 minus 3. It is, here, I'm going to write it like this. I'm going to say this is 3 triangles, so it's 3 times 180, which is 520. Sorry, 540. Okay. Okay. And then, of course, if we want this to be regular, the measurement of a single angle, since there would be 1, 2, 3, 4, 5 angles, would be 540 divided by 5. Right. Okay. Okay, so this would be 108. Right. And so, what am I noticing here? So then for a regular p-gon, the so the total interior angle sum is the number of triangles I can make, which is, so for 4-gon I could split it into 2 triangles, for 5-gon I could split it into 3 triangles, and so the total number of triangles is the number of sides minus 2, so 5 minus 2 here would give us 3 triangles. So this is p minus 2 times 180 degrees over, so this is the total interior angle sum, is p minus 2 times 180. Thus, a single angle is p minus 2 times 180 over the total number of sides, which is p. Okay, so a single angle in a regular p-gon. Okay, so returning to our question, if we have some number of angles meeting at a vertex and we need them to sum to 360, rephrasing this, so if Q such angles meet at a vertex of a tiling, we need the sum of those Q angles to equal 360. Or else there's a gap in your tiling. But another way of saying this is that we need Q times P minus 2 times 180 over P to be equal to 360. Now, if I divide, multiply, and simplify, this simplifies to the following. This simplifies to me needing 1/2 to be equal to 1 over P plus 1 over Q. Where have you seen that before? Dan, the question of triangles. So triangles being the simplest polygon yield, that means that essentially any polygon is built of triangles. And in fact, even for more complicated things, so surfaces, right? Surfaces necessarily are usually continuously defined, right? So a typical surface you might come across sitting in space is the graph of a function of, say, 2 variables, right? That's nice, right? A nice function. But the problem is that, of course, a computer dealing with that, like how do you make that amenable to a computer actually generating things like this? It's actually easier to deal, usually, it's easier to deal with some discretized form of that surface, which involves triangulating the surface. So a surface like that has what's called a triangulation, which is basically an approximation where instead of this thing being smooth, it's replaced with a bunch of triangular faces. So this weird type of polyhedra, or this open polyhedra, is used in space. And of course, the smaller the triangular faces you allow, the closer this approximation can get to the actual surface. And so you can turn any question in 3D into a question of summing up quantities involving a bunch of triangles. Is the brute force, like, crude way of thinking about it. So where have we seen this before? This is like an Egyptian fraction problem, right? And so we need 1 over P plus 1 over Q to be equal to 1/2. But P and Q, P, remember, is the number of sides of the polygon, and Q is the number of polygons meeting at an angle. Or at a vertex. Okay, and so if P is the number of sides that the polygon has and Q is the number of polygons meeting at a vertex, We need 1 over p plus 1 over q to be equal to 1/2. This puts a severe limitation on what can happen here, right? So which are the p's and q's that this works for? It turns out that quickly you figure out there's only 3, right? There's only 3 pairs. So this only works when p is 3, 4, or 6, and then the number of polygons meeting at a vertex would be 6 in the case of p equals 3. P equals 3, these are equilateral triangles. P equals 4, these are squares, and there's 4 meeting at a vertex. And in the case of regular hexagons tiling the plane, you get 3. And so you get 3 cases here, right? So this is tiling by equilateral triangles. This is tiling by squares. And this is by regular hexagons. Okay. Okay, so then what is the... So first of all, this was well known to the Greeks, was well known to the Pythagoreans. And so this was the idea of building the entire plane out of regular polygons. Okay, and these were the 3 ways to do it, and these are the only 3 ways to do it. Okay, so now the question is, can I build space similarly using the object that is the analog to regular polygons in the plane, regular polyhedra. So regular polyhedra. Okay. And so constructing these regular polyhedra, so it turns out that there's a little bit of a difference here. So the difference is that for the regular polygons, there are infinitely many types of regular polygons I can cook up. It's just that not all of them tiled the plane. But it turns out that the number of regular polyhedra is limited just by the conditions we impose on them alone. Okay, and so what are the regular polyhedra? So these are going to have names. So regular polyhedra are going to be called Pythagorean solids. They're more frequently called Platonic solids, and I'll mention why in a second, although these were known to the Pythagoreans, so they predated Plato. So the regular polyhedra are also known as Pythagorean solids, or Platonic solids. And these will be well known to those, let me grab one of them. I have some, but I'd have to dig through some stuff, so I'll just show a picture. These solids, of course, are well known to D&D enthusiasts because you will know them as the shape of your die, right? Of a full set of dice. So what are they? So what are the regular polyhedra? So one is the cube. Okay, this is not the one with the smallest number of faces. This is just the simplest one, right? So what is the cube? So the cube has 6 faces. All of the faces are identical. So identical squares. And you have 3 edges at each vertex. Okay. I have to dig out here I have a simple cube. Let's dig out dice tray, right? Here's cube. Everybody knows what a cube is. And look, we even have labeled the number of faces. They're all identical squares, or they should be if these didn't have rounded corners here. The vertices are 1, 2, 3, 4, 5, 6, 7, 8. So there's the 8 vertices. There are edges connecting each pair of vertices of the opposite faces. So fix a top and bottom, right? Those are your opposite faces. You have lateral sides that are identical squares. And you have, so 6 total faces, 3 edges at each vertex. So if I look at a vertex here, it can be hard to see, but I have 1, 2, 3 edges at each vertex. Okay. All right, so that's the cube. Now, what else? So of course this is known as D6, right? This is a 6-sided dice. There's the tetrahedron, which I don't have one. I'd have to dig. So this is 4 faces. This is the smallest. So 4 faces that are equilateral triangles. Right, 3 edges at each vertex. So this is like a pyramid that has an equilateral triangle as its base. All right. So I'm going to stop here for a second and say, what's the obvious, like, what's the thing we're building here? So the thing we're building, these regular polyhedra, they are these 3-dimensional solids that must be made up of, they must have faces that are regular polygons, so they involve regular polygons. But of course, think about how you would go about building these, right? So putting these together, there would be some restrictions because of the way that they fit together. In fact, you would have to know at every vertex what angle you get with how many you're fitting together, because if it took too many, right? If you had too many things coming together at a vertex, it could flatten out, right? And if it flattened out, then you couldn't close your shape, right? So when is it flat, right? At a vertex. Coming together at a vertex, you have too many and it's flat, then what you would get is that at that vertex, those things would sum to 360. Okay, so we would actually want them, so that this thing closes up, we want that angle sum at a vertex to be less than 360. So we'll see exactly what this means later. Okay, and so there's why did I jump directly to 4? So there's the octahedron, which is a D8, right? So 8 faces. Right? And the 8 faces are 8 equilateral triangles. And you have 4 edges at each vertex. So take 2 square-based pyramids and glue the bottoms together, right? Glue the bases together so that the apex points are on opposite sides. All right, of course, there's the icosahedron. So these were the 4 that were definitely known to Pythagoras. The Pythagoreans discovered the 5th one, but it's actually unknown, and it's thought that Pythagoras himself did not know about the last one. So the icosahedron is 20 equilateral triangles. So 20 equilateral triangles, 5 edges at each vertex. What does an icosahedron look like? It's a D20. It's a 20-sided die. Okay. This is what an icosahedron looks like. Okay. So again, you can see at a vertex how many triangles come together. Oh, 5. Right? And so at a single vertex, there's 5 edges. Okay. Yep, that's how it goes. Oh, I got a 17. Oh, okay, no really good luck today. All right, so the 5th is the one that was discovered last. So this is the dodecahedron, and I don't have an example. I don't have one, but it's a D12, so it's 12 faces. They're regular pentagons. And you have 3 edges at each vertex. Okay, and so quick picture. All right, boom, that's what they look like. All right, so it's a good drawing of all 5 of them. All right. Immediate question is, well, is that all of them? Right? So, fact, there are no more. There are no others. So this is all. Okay, you can't form a regular polyhedron any other way. So this is the list of 5. Now, a couple of things. So we'll see in a second why there are no others, why you can't do it in any other way. But the question is, why, if you've heard of these before, and not just from D&D, but if you've heard of these before, and in any context, it's likely you've heard them referred to as Platonic solids, and I usually call them Platonic solids as well. So why are they called Platonic solids? Because Plato discusses them at length in the Timaeus. So maybe I'll start a new page. So Plato discusses them at length in the Timaeus. And so what is Plato talking about when he talks about them? His idea explained how the physical universe is composed of the Platonic solids. Basically, the idea was that, or Plato's idea was that the Platonic solids built the physical universe. You could build up the physical universe and describe it entirely in terms of the Platonic solids. Okay, of course, he didn't call them the Platonic solids, but these Pythagorean solids, this is a very Pythagorean idea, of course, that the entire universe could be built up with these things. But that is the idea. And so, for instance, specifically, the cube is associated with earth, the tetrahedron is associated with fire, the octahedron is associated with air, the icosahedron with water, and the dodecahedron was associated with the whole cosmos. It's probably because it came last and it was the hardest to discover. In fact, as I'll mention, the dodecahedron is the subject of the very last book of Euclid's Elements. So Plato explains the boiling of water by means of a almost chemical equation, which he wrote as Plato's chemical equation of boiling of water. His chemical equation of boiling water was this. So this is the notation I'm using following our textbook. So what he didn't use this notation, but this is basically what he was saying in words. So it was fire with 4 faces plus water with 20 faces. So it's the icosahedron and so it's tetrahedron and icosahedron. This combines to produce that is 2 air atoms. So these are 2 octahedron atoms and 2 tetrahedron atoms. Okay, so 2 fire atoms, so each with 4 faces. So these are balanced, right? Notice these are balanced in terms of the number of faces that show up here, right? The quantities. So this is very, very much a Pythagorean idea, trying to understand physical universe in terms of these objects. So the dodecahedron was likely not known to Pythagoras. Possibly apocryphally discovered by Hippasus, I believe. Yep. So Hippasus was born 470 BC. And so supposedly the story with Hippasus, and he has something else attributed to him, which is also probably not that likely. So Hippasus was supposedly the one thrown overboard as well later. But the first supposed sin of this guy was that he discovered the dodecahedron, but didn't attribute it to Pythagoras. And so this was his first mark against him, and he was either expelled or supposedly reprimanded in some way from the Pythagorean order because he didn't attribute his discovery to Pythagoras. Okay, and so why are those 5 the only ones? So remember that equation we had for computing which tilings of the plane were allowed by regular polygons. Well, it turns out that this question of what is allowed to happen at a vertex, right, and the fact that we don't want the flattening out to occur. The flattening out happens when this angle sum here is equal to 360. So notice that there's a curving down, which allows this thing to close. And so we want this angle sum to be less than 360. So actually all it takes is me looking at that equation I had written before, and instead of wanting equality, I actually want that inequality. Right? i.e., right, because this simplifies in the exact same way, I want 1/2 to be less than the sum of 1 over p plus 1 over q. Okay. And it turns out there are only 5 possibilities of p and q. So there are only 5 possibilities of p and q satisfying this. And it's exactly the ones that give us those 5 Platonic solids. Okay. Okay. Now, here's a quick table listing exactly this fact. Here. So here's p and here's q. So p is the number of p is the number of sides. Q is the number of angles coming together at an edge. At a vertex. It's the number of edges coming together at a vertex. And p is the number. P is the p-gon itself, right? It's the number of sides of a polygon coming together at one of these vertices. So notice that 3 of the Platonic solids have triangular faces, right? And one of them has square face, that's the cube, and one of them has pentagonal face, which is the dodecahedron. Okay. All right. And so this table also computes the total number of edges in these polyhedra, the total number of faces, which we already knew, and the total number of vertices. Okay. So look at this chart and see if you notice anything. Okay. Well, f plus v is 8, which is 2 more than the number of edges. So 6. 8 plus 6 is 14, which is 2 more than the number of edges for the octahedron. F plus v for the cube is also 14, which is 2 more than the number of edges. 20 plus 12 is 32, which is 2 more than 30. And 12 plus 20 is 32, which is 2 more than 30. And so in all cases, from that table, we get the following. E plus f, so the number of edges plus the number of faces. Usually it's actually written f plus e here. Maybe I should do that just to stay in order in terms of the dimension here. So the number of faces plus number of edges minus the number of vertices is equal to 2. Right? Oh, wait a minute. This is not what I said here. Oh my god. Why am I doing this? It's faces plus vertices minus edges. Okay, is equal to 2. I'm confusing myself because this is an alternating sum if you go in order of dimension. So the faces are dimension 2, the edges are dimension 1, the vertices are dimension 0. So keeping them in order, the actual way to write this would be f minus e plus v is equal to 2. Either way, this is Euler's formula. Okay, so this was not proven until the 1700s, but this was known to Descartes probably. It's unknown whether the Greeks had actually noticed this pattern that shows up in that table. The reason why this works is actually a really, really deep fact that I hope to get to by the end of the semester, but I'm not sure that I will. So this works for a very interesting reason, though. One more thing I will say is, and then I will move on to the last thing I wanted to discuss about the Pythagoreans, which was how they dealt with the incommensurables. So one more thing I wanted to discuss is that book 13, which is the last book of the elements, so chapter 13, the elements dealt with the Platonic solids, but specifically, so dealt with the Pythagorean solids. Specifically, yeah, there we go. Specifically, the Dodecahedron. Well, I mean, it dealt with all of them, but it even worked out the Dodecahedron. The thing that it specifically was curious about, or the thing that it was investigating, was it was the question of inscribing or circumscribing these regular polyhedra. So, and the question of, so this is the question of circumscribing the polyhedra in question. So what do I mean? Basically, consider any of those Pythagorean solids. Euclid showed that you could come up with a sphere, okay, that contained those. So you come up with a sphere, fixed radius, that contained those Pythagorean solids in the sense that all of the vertices lied on the sphere. So looking at the icosahedron, it's got a lot of vertices here, but there exists a sphere of fixed radius such that each one of these vertex points lies on that sphere. And Euclid actually even computed the ratio of, or the relationship rather, between the radius of that sphere and quantities on these Pythagorean solids. So, for instance, even this, if you look at the cross section of the icosahedron. Okay, so for instance, if you have icosahedron, now I'll bring it closer. So you have icosahedron like this. If you look at a cross section of the icosahedron that intersects 6 faces, the cross section in question, so it's hard to, so here you see, here would be an edge, here, 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 and here. So if I imagine a plane cutting through those 6 faces, what I would get is a hexagon. That hexagon looks like this. Okay, that's the cross section I get. And if we take this length AF to be unit length, then this length from, if I drew in this line segment from A to C or from F to D, the length of that segment is the golden ratio. Okay, so the way to think about this is the ratio of that segment cutting through from that edge. And you can do this, of course. So if you look at the icosahedron, say from this vertex point to this one, that and this distance are in ratio that is the golden ratio. Okay, that's one of the things that was computed in this last book of the elements. Okay, so that was kind of, at the end there was just kind of a random smattering of facts about that. Again, you know, some of those things weren't known until after the Pythagoreans. So some of that stuff wasn't known until Euclid, but at least, you know, the interest in those Pythagorean solids dates all the way back to Pythagoras. So, the last topic involving the Pythagoreans directly is the crisis of incommensurables, which was, as I mentioned before, their discovery that not every length is commensurable. So this word here, so a length, or I should say two lengths, A and B, are said to be commensurable if there exist positive integers P and Q such that the ratio of the lengths is equal to the ratio of those integers. Now, here is a thing that I'm going to spend a decent amount of time talking about this, not just now, but later when we talk about Euclid again. You might think that this seems like a very silly distinction, because for us, the lengths A and B, we treat them as honest-to-God numbers, right? So if I tell you that I have two lengths and one is, say, 5.2 and the other is 7.35, right? Then forming the ratio A over B, well, I already have the numbers are the lengths, right? But the Greeks made a distinction here because the lengths were this geometric object, right? And taking a ratio was a thing that they did geometrically, right? Not really algebraically. And so having integers that were in the same ratio as the lengths was important because that is how the Greeks dealt with everything. And this is going to tell us why it was such a big deal that there existed irrational numbers, because the Greeks didn't have infinite decimals. So something like square root of 2, for instance, that being irrational was bad because they had no way to algebraically deal with it. They couldn't write out infinite decimals because they didn't have a notion of that. And then they were, because of this problem, we're going to see the square root of 2 is not commensurable, right, with other lengths. And so they had to come up with a very sophisticated way of dealing with these ratios. Using modern language, they treated these ratios as equivalence classes. And this was due to Eudoxus, who I'll talk about later. And this is what Book 5 of the Elements is entirely about, is just how to deal with handling algebra of quantities that might not be commensurable. So even in the time of Euclid, which was, almost 200 years after the Pythagoreans were struggling with this, this was still something that the Greeks, were struggling with, and Euclid had to devote an entire book of the Elements just to be able to make sure that all the algebra could be done. Because without that, when you're dealing with irrational quantities, which of course show up all the time, it was an issue. So the big fact, right, that is very, very bad for the Pythagoreans. So the diagonal of unit square ABCD having side lengths all 1, okay, is not commensurable with its side. And so, as I said, this shows up immediately. Unit square is one of the simplest geometric diagrams you could have, right? And in unit square, its diagonal is not commensurable with its side. So immediately you get an incommensurable. Okay? And so, to prove this, right, well, by the Pythagorean theorem, this diagonal has length square root of 2. Right? Because it's unit square, so one side is 1, another side is 1. The diagonal is the hypotenuse in that right triangle. So 1 squared plus 1 squared is equal to c squared. Right? And so c has to be square root of 2. Okay. So then I want to show that there cannot exist positive integers p and q such that square root of 2 over 1 is equal to p over q. Right? Why do I want to show this? I want to show this because I'm trying to show that it's not commensurable with its side, right? So I have diagonal has length square root of 2 by the Pythagorean theorem. If it's commensurable with its side, then it would mean that square root of 2 over 1 is equal to p over q for some positive integers p and q. So I want to show that this can't happen, i.e. square root of 2 equals p over q. And so, what's the best method of doing this? Best method of doing this is to suppose that this is true and derive a contradiction, because something can't be true and false at the same time. All right? And so, how do I do this? You've probably seen this before, but if you haven't, then I'm doing it regardless. So, suppose that p and q are positive integers such that square root of 2 is equal to p over q. Okay. Now, maybe p and q have some factors in common. All right, we know that the way that fractions work, I can reduce fractions and I keep the same fraction, right? So we can assume this fraction is in lowest terms. I.e., that the greatest common divisor of p and q is 1. Another way of saying this is to say that p and q are relatively prime. Okay, so this fraction is in lowest terms. That's something we can assume. We've already done all the reducing, all right? We can always do that for a fraction. Okay, so what does this mean? I can square both sides here. So squaring both sides, whatever this number is, I'm using this as a symbol. I don't have to write root 2 here. It's just a symbol. And what this symbol means is that it's a number such that when I square it, I get 2. So squaring both sides, I get 2 is equal to squaring this fraction, I get p squared over q squared. Right? And by basic algebra, this tells me that 2 times q squared is equal to p squared. So p squared is equal to 2 times something. So I don't care what the something is, it's just a positive integer. So p squared is equal to 2 times something. But if an integer is equal to 2 times something, well, that's just another way of saying that p squared is even. Right? But if you have a number and when you square it, it's even, the only way that can happen, right? And p is a positive integer, and not just any real number. P is a positive integer. When you have a positive integer and when you square it, you find out that it's even. The only way that can happen is if p itself is even. But by definition, if p is even, what this means is that p is equal to 2 times k for some positive integer k. Well, plug this into the equation I have here. Then 2q squared is equal to 2k squared. 2k squared, though, is 4 times k squared. Dividing by 2, q squared is equal to 2 times k squared. So q squared is 2 times a positive integer. But that means that q squared is even. Since q is a positive integer, the only way this can happen is if q is even. Oh, but now we're in trouble, right? We started out with an assumption that this fraction, p over q, was in lowest terms. But then I found out that both p and q are even. Well, if both p and q are even, then what could I do to reduce the fraction p over q? I could divide both by 2. That would further reduce the fraction. What this means is that the GCD of p and q is greater than 1. It's at least 2, right? But that's a contradiction. This is a contradiction, right? You cannot have the GCD of p and q be 1 and simultaneously be bigger than 1. So something's got to give, and the only bad assumption that we've made, the only assumption here that we've made at all, everything else follows logically, the only assumption was this first thing we started with. Suppose that p and q are positive integers such that square root of 2 is equal to p over q. Therefore, this assumption cannot be possible, right? Thus, there exist no such integers p and q. Such that square root of 2 is equal to p over q. So that's it. Okay. And so we would say that square root of 2 is irrational. Right? That's how we would say this. Now, the thing is that this was certainly discovered, and this proof was certainly discovered by the Pythagoreans, supposedly by the same Hippasus that discovered the Dodecahedron and was, summarily tossed overboard. But this is certainly known to the Pythagoreans, and this was kept secret by them because this certainly didn't help their philosophy that all was number, meaning all was whole number and ratio of whole number, right? Because this shows, oh wait, there's this other type of number that is not a ratio of whole numbers. Okay, like here it is. And so the Pythagoreans actually tried to keep this secret. And the reason for doing so, as I mentioned, was that the Greeks had computational difficulties with a thing like this because they didn't have a decimal system that allowed for infinite decimal expansions. And so algebraically, they just did not have the tools to deal with it. And so I'll talk about later what they managed to do to handle this algebraically. And I'll also explain a little bit next time why everything they did was tied in with geometry. So their algebra was like completely entangled with their geometry. And so if they couldn't handle it geometrically, then they basically couldn't do it algebraically. So I'll show some examples of that next time. I'll also mention the Pythagoreans actually approximated square root of 2. So just like the Babylonians, they approximated square root of 2, or they came up with a process that allowed for approximating square root of 2 as accurately as you want by rational numbers. But of course, this is still an approximation. And then I'll say some more about some of the philosophical developments in Greek math before talking about mathematics in Athens, of which there's a lot to discuss. And then we are basically barreling through to, we'll talk from there about Plato and Aristotle, and then from there we'll get to Euclid, and then later antiquity mathematicians from there. So we are going to be with the Greeks for quite a while going forward, and that's how it is because we owe them a lot. So anyway, I posted the homework Yesterday, the deadline's not super strict, so if you need more time, just let me know, and feel free to ask questions in the chat if you have specific questions about the homework. So anyway, I will see you all on Wednesday, where we continue on our investigation of Greek math.